Hello everyone, in today's video we'll be seeing these questions from the year 2022 paper 1. So let's see the first question. In first question we are given a 1 mole of gas which obeys the van der Waals equation. So if its molar internal energy which is given as Ct minus A over V, which is dependent upon temperature and the molar volume V. Here A and C are the constants, so we have to find out the molar heat capacity Cv and Cp for this gas. So let's see how we will do this. So we are given 1 mole of gas which follows a van der Waals equation of state, which is P plus A over V square, V minus P is equal to RT. And we are given the molar internal energy expression, which is Ct minus A over V. So we have to find the molar heat capacities at constant pressure and volume. We will first find the Cv. So let's use the first law of thermodynamics. Which is dq is equal to du plus dw. So this dq is equal to du plus pdv dq. Then we have to differentiate this with respect to temperature at constant volume. So the expression will become like this. This will be 0. So this dq over dt is Cv. And this is, we know the expression for u. We just have to differentiate this with respect to temperature at constant volume. Here volume is constant. So the second term is constant. So our differentiation is C in this case. So let's find the Cp now. Similarly, differentiating this first law of thermodynamics with respect to temperature at constant pressure now. So this will give us du over dt at constant pressure, and this P is constant, so we can take out this P, dV by dt at constant pressure. So we will find out du by dt at constant pressure first. So this is Cp. So this will be Ct minus A over V at constant pressure, and this P dV by dt at constant pressure. So let's move to the next page. So this is the expression we got till here. So let's do the differentiation with respect to temperature. So we will get C here, and this will get minus 1A over V square del V by del D at constant pressure, and this is the second term. So let's rewrite this expression as C plus P plus A over V square, and we will take this del V by del T at constant pressure common. So we will mark this equation 1 here. So let's find del V by del T now at constant pressure. So to find this, we will use this van der Waals equation. So let's differentiate this van der Waals equation with respect to temperature at constant pressure. So differentiation of first term, this is P plus A over V square at constant pressure, and second term as it is, and then first term as it is, and then differentiation of second term at constant pressure, and this will be R. So let's differentiate this. So P is constant, so we will differentiate the second term. So this will be minus 2A over V cube del V by del T at constant pressure, and this is V minus V plus PA over V square, and this is V del V by del T at constant pressure, which is equal to R. So let's move to the next page. So this is the expression. So let's take del V by del T at constant pressure common. So this is P plus A over V square, and this is minus 2A V minus B over V cube. and this is R. So let's take this whole bracket on the other side. So this is P plus A over V square minus 2A V minus B V cube. So this is expression. Now we will put this expression of del V by del T at constant pressure in this Cp expression. So this Cp is equal to C plus P plus A over V square, and this R over P plus A over V square, and this 2A V minus B over V cube. So let's divide this. So rearranging this, we will get R, and this will be 1 minus 2A V minus B V cube, and this is P plus A over V square. And we will replace this P plus A over V square. This will become C plus R over 1 minus 2A V minus B whole square, and this is RT V cube. This is the expression. So let's move to the next page. So using binomial expansion for this denominator term, so this will become Cp is equal to C, and this R, so its power, negative power, will gets multiplied with the second term. So our term will become like this. So Cp is equal to C plus R 1 plus 2A V minus B whole square, and this is RT over V cube. So this is our molar heat capacity at constant pressure. So this is a solution for our first question. Now let's see the second question. In second question, we are given a compressor which is designed to compress air. So we use that compressor to compress helium instead of air. So it is found that the compressor overheats, and we are given the gamma for both helium and air, and the initial pressure is same for both, and the process is adiabatic. So let's see. So we are given these things. We are dealing with ideal gas, PV and RT, and this is the adiabatic compression. So initial pressure of air and the helium is same, and we are given the gamma for both. So gamma for helium is more than the gamma for air. Since the process is adiabatic, so we know the relation between P and V. So PV gamma is equal to constant. So let's start with for air. So for air, we will write this as PF, final pressure and volume, and this is initial pressure. So this will be constant for final and the initial position. So this PF for air is equal to P naught for air, and this is V naught over Vf gamma air. Similarly, we can write for helium also. So this is PF for helium is equal to P naught for helium, and this is V naught over Vf for helium. So let's divide this to equation. So divide 1 and 2. So this PF for air over PF for helium will be equal to P naught for air. This is V naught over Vf. This is gamma air, and the denominator is P naught for helium, and this is V naught over Vf gamma helium. So we are given the initial pressure for air and helium are the same, so we can cancel this, and we know our gamma for helium is more than gamma for air. So our pressure, this P final for helium, is greater than P final for air. So we can say the final temperature for helium will be greater than final temperature for air. So that's why we see overheating in the helium case. So this is a solution for our second question. So let's move to our last question. In C part, we are given a gas of interacting atoms has an equation of state. This is PTV, how the pressure is varying with temperature and volume. And there's a heat capacity which also depends upon temperature and volume. Here all A, B, C, D, E, F are the constants which are independent of T and V. So we have to find out the differential of internal energy in terms of dt and dV. So here we are given the expression for pressure and the heat capacity at constant volume. So we have to find the differential of internal energy in terms of dt and dV. So here U is a function of T and V. So we can write this internal energy differential, this du, which is a function of temperature and volume, in the form of differential. So it's del u by del t at constant volume dt, and this del u by del v at constant temperature, and this is dv. So we have to find out these two differential in order to get this differential of internal energy in terms of dt and dv. So let's find out the du by dt. So we know this dq by dt at constant volume is equal to del u by del t at constant volume, so which is equal to Cv. So this is simple. Now let's find out the del u by del v at constant temperature. So let's use the first law of thermodynamics. This is dq is equal to du plus pdv. So we can write this dq as tds. This is du plus pdv. So now let's differentiate this equation with respect to volume at constant temperature. So this will be del u by del v at constant temperature, and this is p del v by del v at constant temperature. This will be 1. So del u by del v at constant temperature is equal to T del S by del V at constant temperature minus P. So we will be using this Maxwell equation, del S by del V at constant temperature is equal to del P by del T at constant volume. So let's use this Maxwell equation here. We get T del P by del T at constant volume minus P. So we have find out this del u by del t and this del u by del v at constant temperature. So we will put these two expressions in. So we get this expression after putting this del u by del t at constant volume is Cv, and this del u by del v at constant temperature. So let's find the del p by del t first. Del p by del t at constant volume. So we are given this expression of pressure in the terms of T and V. So let's differentiate this. So we will get half A, this is T half, and this is 3B T square, and the other one is constant, so this will be 0. So now let's multiply this with temperature. So because we need T del P by del T at constant volume. So after multiplying this with, this will be A by 2 T half, and this with 3B T cube. So we get this. So now subtract this pressure from this whole term. So we will get A by 2 T half plus 3B T cube minus pressure will be A T half minus B T cube minus C B minus 2. So this will be minus A by 2 T half, this is plus 2B T cube, this is minus C V minus 2. So this is our whole term. So this du, the differential of internal energy in terms of temperature and volume, will be Cv. So let's write, because it is Cv dt, Let's write the CV expression. This is d t half plus e t square v plus f t half, and there's dt, and the second term is minus a over 2, and this is t half plus 2b t cube minus cv minus 2. This is dv. So this is our expression for internal energy differential in terms of dt and dv. So this is the solution for our third question. If you have any doubts related to any of these questions, you can write me in the comment box. If you like this video, please like, share and subscribe to my channel, and thank you for watching this video.